Hello. In this video, we're going to do a curve sketching example. We've been given the function fx and the derivative f prime and the second derivative f double prime. Now, before we start off any curve sketching question, we want to ensure that our functions are fully factored. Often they are, but sometimes they're not. And so if we take a look here, the denominator x squared minus 1 unfortunately hasn't been factored. And so we want to factor that as x minus 1 and x plus 1. Similarly over here, we're going to have x minus 1 squared and x plus 1 squared. And here we'll have x minus 1 cubed and x plus 1 cubed. It's important that we factor each one of these denominators so that when we're drawing the sign diagrams, we have all the relevant key points so we can draw them properly. Now, there's many ways to approach a curve sketching question, and often on a test or on an exam, they'll actually tell you what they want from you, whether it's domain, range, intercepts, and the like. What I'm going to do is try to provide all the different steps that you might need in a question like this. And so I'm going to do my best to exhaustively find all the different portions of this graph they may ask for. So the first thing I'm going to do is find the domain. Now, how would we find the domain of this graph? If you take a look, what are the values that would be undefined that we couldn't plug into the function? Not the derivative or the second derivative, mind you, just the original function. And if you look here, you're always looking for either square roots, where you can't square root a negative number. You're looking for denominators, where you might accidentally divide by 0, those types of things. So if you look here, when x is 1, that will give you a 0 in the denominator, which is not good, or when x is minus 1. So both of those are going to be not in the domain. But the domain will be everything else. So we can write minus infinity to minus 1, union minus 1 to 1, union 1 to infinity. All right, next up we can look for maybe an x-intercept or a y-intercept. The x-intercept looks pretty clear. That will be 0. And looks like that point 0, 0 is actually going to be the y-intercept as well, because when you plug x equals to 0 in the original function, you get 0 over negative 1, which is 0. So the x-intercept and the y-intercept are both happening at the same point. They're happening at the origin. So just a little interesting thing to note there. Now, there might be some horizontal or vertical asymptotes, and we should investigate those. The horizontal asymptotes are easy enough to find. We can use the quotient theorem to find those. So what we do is we find the limit of the function, the limit as x approaches infinity of the function, so x over x squared minus 1. Applying the quotient theorem gives us the following: the limit as x approaches infinity of x over x squared. We can cancel out one of those x's, giving us 1 over x, which of course will limit to 0. Now, this doesn't happen often, but every once in a while there is a different limit as x approaches negative infinity, and so for completeness, we're going to approach negative infinity as well. In our case, the quotient theorem will still apply, and because we don't have any kind of absolute value or root going on, we're still going to have x over x squared, which is still going to simplify just as nicely to 1 over x, which again gives us 0. So here we have a horizontal asymptote at y equals to 0. Now, to find the vertical asymptotes, it's often useful to actually have the sign diagrams available to us. And so that's what we're going to do now. We're going to go ahead and draw the sign diagrams. So we have f, f prime, and f double prime. Now, if we look back at the original functions we were working with, we can see that for fx, we have a 0 at 0, and we have 2 undefined or NPVs at 1 and minus 1. So for our sign diagram, we'll have the following. We'll have undefined at -1, and at 1. And we'll have a 0 at 0. Now if we pick a number bigger than 1, let's take a look at what happens. So a number bigger than 1, say 10, this will be positive, positive, positive. So overall we're going to have positive, giving us the following sign diagram. Positive, negative, positive, negative. We could go on and finish the other sign diagrams, but I'm going to use the sign diagram right now to help us determine the vertical asymptotes. And so because these points here, NPVs, or they're not part of the domain, you're dividing by 0, all those types of ideas, those are going to be where our vertical asymptotes are happening. And so all we have to do is look at the sign diagram and say, well, here we have a vertical asymptote. On the one side we have a negative sign, on the other side we have a positive sign. This will tell us what's happening at that horizontal or at that vertical asymptote, where the function is going either to positive infinity or negative infinity. So let's go ahead and do that. So we'll find the limit as x approaches negative 1 from the left of x over x minus 1, x plus 1. Because the sign diagram tells us it's going to be a negative value here, and of course when you plug this in you get negative 1 over 0, it's undefined, we know it's going to be some type of infinity, and the sign diagram is telling us that it's a negative infinity. The same logic will apply for all the other limits we need to investigate. So the limit as x approaches negative 1 from the right of x over x minus 1, x plus 1, will now equal positive infinity. And so this here is going to be our first vertical asymptote at x equals negative 1. We do the same thing, the limit as x approaches 1 from the left of x over x minus 1, x plus 1. Looking at that sign diagram, we can see that on the left side of 1 we have a negative value, so we're going to be getting negative infinity. And finally, the limit as x approaches 1 from the right of x over x minus 1, x plus 1 will equal positive infinity. And we have ourselves another vertical asymptote at x equals positive 1. Now we can continue on with the sign diagrams we are working with. We can go ahead and find the sign diagram for f prime x. So again, if we look back at our original f prime, we can see that in the numerator there's nothing going on in terms of zeros, but the denominator does have those 2 points there, x equals 1 and x equals minus 1. They're undefined. And because there's a 2 on them, they're going to be an even power. So we write that in our sign diagram just like this. We put a hole at negative 1 and a hole at 1. And we draw vertical lines to indicate that they are even powers. Notice again how I'm drawing these roughly in line with fx so that my sign diagram can give me as much information as possible, trying to draw it to scale to what I've already written down. Now again, going back, we need to pick a value bigger than 1. So let's say 10. The numerator will be positive, and here we'll have positive and positive, but this negative sign overall will make it negative. So that will give us the following sign diagram. Negative. Even power means we keep the same sign, so negative, and negative again. Finally, we need to find the sign diagram for f double prime. Looking back up here, we can see that there's going to be a 0 at 0. There's going to be undefined at 1 and minus 1. If we pick a value bigger than 1, say 10, we're going to have positive, 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 so it will be overall positive. So let's go ahead and finish off our last sign diagram. So we're going to have our 0 at 0, undefined at 1 and minus 1. We said it was positive, negative, positive, negative. Now on f prime and f double prime, these negative and positive signs mean something. For f prime, this means the function is decreasing. So we draw that with a line going down. And for f double prime, this means the function is concave down, concave up, concave down, and concave up. Now looking at the first derivative, it doesn't appear like there's any relative minimum or maximum. But looking at the second derivative, it looks like this point here at 0, it's changing from concave up to concave down. So this is definitely going to be an inflection point down here. You might wonder about the other points. Are these potentially inflection points? And they might be, but since the original function isn't defined at 1, you can't have an inflection point because you don't even have a point. Now, again, on a test or on an exam, you may be asked to take these positive and negative for the function or for the derivative or the second derivative and list them in interval notation. So I'm just going to list one of them here just so you get a bit of a feel for it. So let's do f prime. And so we could say, where is the function decreasing? Well, that will happen wherever the derivative is negative. So we could say it's decreasing. And it looks like it starts off at negative infinity, continues on to negative 1, union. Then it looks like it decreases from minus 1 to 1, union, and then 1 to infinity. You would also be expected to do the increasing, concave up and concave down, but I'm just going to omit that for now. Now let's go ahead and actually draw this graph that we've been so diligently finding the information for. So it's nice to draw a set of axes. And of course we should give them some labels. This is x, this is f of x. We can put our asymptotes down here. And so we have our horizontal asymptote at y equals to 0. We have our vertical asymptotes at x equal to 1. And we have another one at x equal to minus 1. Finally, we can put any points that we know. We do have this nice point here at 0, 0. We know this is an inflection point. We know it's a y-intercept and x-intercept. So we can label this point 0, 0 as an inflection point. Now, all that we really have left to do is sketch the graph. And so we can start over in the far left, up in quadrant number 2. And so what do we have? Well, we know the function has to be decreasing. And if we take a look at the information we found from our vertical asymptotes, we know that for x equals to negative 1, on the left-hand side it should be negative infinity, and the right-hand side it should be positive infinity. So we can encode this information into our graph as follows. We know that down here, we should expect it to be at negative infinity. Over here it should be a positive infinity. In this section it should be decreasing, and we should have a concave down shape. Over here it should be decreasing with a concave up shape. And so that should be enough to get us the first portion of the graph as follows. Now, when it hits the inflection point, it goes from being concave up to being concave down. So we can change the concavity and approach the asymptote. Over on the other side of the asymptote, we can still see, as x is approaching 1 from the right, it should be up at positive infinity. And we should have this concave up shape as we approach the asymptote. So we can draw that final section into the graph. And we're good to go. It's always helpful to compare the graph to all the sign diagrams, in particular the f of x sign diagram. And so if you take a look here, the function was supposed to be below the x-axis, then above the x-axis, below the x-axis, and above the x-axis. If we compare that to what we have, we can see that the function is below the x-axis, above, below, and above. So our sign diagram for fx, for f prime x, for f double prime x, all agree with one another, and they all line up to give us this graph. Again, you may be asked a few other questions about the graph, such as the range. In this case, you can see that the graph has this middle wiggly shape where it goes all the way up to positive infinity and all the way down to negative infinity. So this graph would have a range from minus infinity to infinity. Or you may be asked other questions. But this is the general scope of a curve sketching question, and so as long as you follow this general method, you should be able to answer any question that comes your way. Thanks for watching.